Excellent. Right, so we welcome back Rujna's illustrious student, Eric. So yeah, please give a warm welcome to Dr. Eric Krotkov.
I hardly recognize myself with that gracious introduction, and I owe it all to Professor Baichi here, who really gave me a chance early in my career and believed in me. And Mama Baichi, you're going to be proud. You're going to see what your kid has done here. So let's see. I am going to give a fairly high-level talk. The problem in being in an industrial research lab is that, there's some of our best ideas we are kind of being proprietary about. The Toyota Research Institute is a little different from lots of other labs. Think of Apple, where you're not allowed to talk with your office mate or your family members about what you're doing. So that's at one end of a spectrum. And TRI is much farther to the other end, but I can't give you all the juicy details here, at least this time. So I'm going to keep it at a fairly high level. And let's face it, the PowerPoint is never the interesting part. It's always the questions and answers. So I'm not going to go on and kill you with PowerPoint. I'm going to leave some time for, an interaction. And if you want to stop me along the way, please do. So TRI's mission is to use AI to improve the quality of human life. So we really mean it. That sounds like such a platitude. It could be on a Hallmark card. But there are two specific ways. Making automobiles safer. There are so many, I think 1.2 million deaths per year and lots of injuries. There's so much room for improvement to really improve the quality of life. And the second one, to go beyond cars, to expand the idea of mobility technology to do things in homes. So that's kind of going to be one of my big themes today. We've already talked in many of our public presentations about what we're doing with driving. I'll give a tiny summary of that. It's kind of already out there. Gil Pratt and James Kuffner have done a great job of spreading the word. And we have not talked publicly about our robotics work until last Saturday. So I'm very pleased to kind of come out here at Berkeley. This is not widely known yet. Do I have a chart about TRI's history? Not really. That's the mission. We were funded with $1 billion, 10 to the 9th, for 5 years. And the goal was to become the DARPA of Toyota. So DARPA, the Defense Advanced Research Projects Agency, has been extremely successful through 5 decades now of being revolutionary and being disruptive. DARPA brought us the Saturn V rocket, which took us to the moon, GPS. My particular part when I was a DARPA program manager was the robots that are used to defuse roadside bombs in Afghanistan and Iraq, the PackBot and the Talon. What else has DARPA done? Well, most recently the DARPA Robotics Challenge was motivated by the Fukushima incident in Japan. And the internet was the ARPANET and the DARPANET before it was the internet.
Very fancy prosthetic arm.
Right, the prosthetic arm that Colonel Ling did. So Toyota knew that they'd been investing in their own laboratories for self-driving cars and robots for decades, and they were falling farther and farther behind the leaders, and they recognized it and wanted to bring in some people from DARPA. The CEO is Gil Pratt, and so he was a program manager at DARPA, and I also had been at DARPA for a long time. A few other DARPA people were all brought in, and we started TRI last year, January of 2016. We had 0 people, and we're now 220 at 3 different locations: Silicon Valley, right outside Stanford University, Cambridge, right outside MIT, and Ann Arbor, right outside University of Michigan. And it's no secret why we put our offices and labs right near those universities. The partnerships with the creative minds and the talent and the students. Well, here I am. I recognize the depth and quality of the work being done here, and we've already started a few projects at Berkeley, and I'm looking for more ideas. That's part of the reason that I'm here. So that's the history of TRI. We are hiring like crazy. We're probably going to open one more big office. And I will say a little bit more about it. Now, our goals. So safety, access, and quality of life. So these 2 are about driving, and this one is about robotics. So that's kind of echoing the previous chart about our mission. So safety, lots and lots of casualties and deaths due to accidents. And we have 2 different, one main approach here, which is iconized there as Guardian. And in Guardian, the idea is that the person drives, and there's a system that is watching, like your guardian angel, watching over your shoulder. And if you're about to do something dumb or dangerous, it will warn you. And if you're really about to do something dumb, it will take over and help you and save you. The other approach here, called chauffeur, is what you classically think of as a self-driving car. You're reading the paper with your hands behind your head, maybe not paying attention, and the car is driving itself. So there's a strong motivation for that, allowing a system that can drive when you're disabled or older, and aging society is going to be a huge, huge problem for first Japan, then China, then United States and Europe. So it is a wave that you can see coming, 1960, 2010, 2060. This side is male, this side female, and these are the numbers of people at different ages. So you can see it's bulging where there are more and more. The greater proportion of society is old. These people are older and they're less able to move, but they don't have less of a need to move, right? They're not just going to stay where they are. So they're going to need transportation help, and chauffeur is going to help meet that need. So safety, access, and I'm going to talk about this more poetically in a slightly later chart. Okay, this one's out of order. I already told you about the background here. So that's our CEO. I started in January of 16 as the chief operating officer, just getting the company up and running. And then we brought in a real professional from Lyft, who was their chief operating officer. And James Kuffner, was a professor at CMU, then went to Google. He's the person who coined the phrase cloud robotics. He went on to write the planner that did the Larry 1K, which was the first Google self-driving vehicle that drove 1,000 miles in the Bay Area. And Kohaya-san is our liaison. So 20% of our workforce is native Japanese, basically Toyota employees who are loaned to TRI. This is our transition path. This is how we get the technology and our inventions and our practices from the United States into big Toyota. And Kohaya-san here is kind of the conduit. And that's a very big job. In fact, it would be great to have self-driving cars and home robots. But if we simply increase the literacy of Toyota and awareness of software practices and make the company a little more agile. It'll be a huge shift for the company. So there's a cultural component to all of this that's very, very substantial. Toyota has 360,000 employees. Last year, its profits were $20 billion. They make 10 million cars a year. There are more cars on the road, more Toyota cars on the roads on the planet than any other brand. We're kind of neck and neck right now with Volkswagen and Nissan Fiat or Renault Fiat to produce the most this year. But Toyota's a big company, a lot of inertia. And Toyota, I talked about DARPA being revolutionary, and we're trying to disrupt the normal business practices. And a lot of Toyota doesn't like that. It's a mosquito, swat it. And his job is to help fan the flames. So I told you about our different locations. And we're going to have roughly 300 people in less than a year, and distributed mostly in Los Altos and equally split between Cambridge and Ann Arbor. And if I didn't say it already, we are hiring. So here's how we organize our research and development. I call it the bullseye diagram, and the slices here are proportional to the amount of effort. So this is the driving effort. And that's led by James, who's very well suited for that because of experience with the Google self-driving systems. And I already talked a little bit about Chauffeur and Guardian, but there's a common core. In fact, if you drew the number of lines of code for Chauffeur, it would be the width of this line and the width of that line, and everything else is really the core. The perception, planning, tracking, prediction, modeling. What is the human in the car going to do? What is the human pedestrian going to do? All of this kind of prediction. That's all in this common core, common piece. I'm responsible for our robotics effort, our materials discovery effort, and this red thing, the university efforts at Stanford, Michigan, and MIT. And there's some core technologies that are equally applicable to all of the application areas. James is responsible for those. And for example, in learning, we're using learning in all three of the areas. So we have our own, I wouldn't call it basic research, it's not 6-1 research investigating basic principles, but we have a lot of people messing with learning systems and not, just trying to make them better, separate from, independent of applying them to driving robotics materials. That's a very unusual setup, but TRI is a little unusual. I think.
Today you're going to see 4 different demonstrations. The first 2 of them are going to be in chauffeur mode. What chauffeur means is that the car drives for you. You would use a chauffeur car if you can't drive, for instance if you're disabled, if you don't want to drive, if the traffic is very bad.
My goodness. Can anyone still hear? I'm sorry to do that to you.
Today you're going to see 4 different demonstrations. The first 2 of them are going to be in chauffeur mode.
Oh, you're going to know the beginning of this by heart.
Today you're going to see 4 different demonstrations. The first 2 of them are going to be in chauffeur mode. What chauffeur means is that the car drives for you. You would use a chauffeur car if you can't drive, for instance if you're disabled, if you don't want to drive, if the traffic is very bad, or if you're taking a taxi cab ride, like mobility as a service. The other 2 demonstrations are going to be in Guardian mode. This is for people who want to drive. It's a safety net against having a crash. We have designed a special test car which has dual steering wheels, dual brakes, and dual accelerators. The reason for this is that we need two different personnel in the front of the car. One is a safety driver. The other driver is a test driver. They are there to interact with the car as if they're the actual driver in a production car. But for our development, this is a tremendous advance because it lets us test the Guardian system with an actual test driver while still having a safety driver there just in case.
We're going to start off with the chauffeur mode of the car, where the car is going to be doing all the driving for us. So you can basically sit back, relax, and enjoy the ride. All right, you ready, Sharon?
Yes, I'm ready. Are you ready, Aaron?
I'm ready.
Okay, here we go.
And one of the real world things that we have to handle in self-driving mode are all the randomness that occurs every day. Actually, in this lab, we're recreating a scenario where we've had a pickup truck drive along the track and actually dump some hay bales out of the back randomly. So what you're going to see is our car senses, does a safe lane change, senses the next one, and also then changes back.
Very smooth.
So what we're going to show you in this lab now is how this car is able to interact with the traffic on the roadway. So as we're coming around the bend here, you'll see that there's another car on the track with us. The car senses it.
Oh, wow. It's right there.
See, we got actually our pickup truck parked in our lane, blocking us.
Oh, no.
So you see our vehicle slow down,
Nice.
tuck in behind that vehicle that was in our blind spot, and then do a smooth lane change back.
That was really smooth.
Pretty cool, huh?
Yeah, very cool.
Now we're going to demonstrate our Guardian system. We're going to emulate what happens when a driver falls asleep. Guardian can tell by using a camera that's part of the dashboard. The camera can even see through sunglasses in order to see what the driver's eyes are doing, or if their head is moving into a position that indicates they're not paying attention. So Ryan, whenever you're ready, why don't you go ahead and pretend to fall asleep. And now Guardian has stepped in, it's driving the car for you, and now it will offer at some point to give it back to you. Why don't you go ahead and take it now. One of the most frightening things that can happen on the highway is when a car in front of you switches lanes to avoid debris. You have very little time to react because your view is blocked by the car in front of you. We have sensors that can see significantly better than a human driver can see. The Guardian is going to take over where a car switches lanes in front of us in order to avoid debris. Here that car switches lanes, Guardian decides we have to switch lanes also, and we avoid having a crash. Now Guardian has offered to hand back control, and Ryan has taken control back of the car. So today you've seen demonstrations of two basic technologies that the Toyota Research Institute is doing research on. This is all part of TRI's work to eventually build a car that can never be responsible for a crash, regardless of what the driver does.
So we did all of that a couple of weeks ago, and Akio Toyoda, the president and CEO, was one of the guys on the second steering wheel. All of our board of directors and biggest investors all had a chance to do it. So I'm happy to. I'm not.
This is in Michigan?
That is at the Gazoo closed course in Texas. So Toyota's North American headquarters is in the Dallas area, and this is a closed course at that facility. So in 2020, we expect to offer rides to athletes, officials, and the public at the Tokyo Olympics in 2020 in these cars. And at the same time, we'll introduce commercially the highway teammate. So that won't have chauffeur or Guardian directly in it. It's really a Toyota Motor Company launch, not the TRI launch. But Olympics in 2020, highway teammate in 2020. In the early 2020s, we'd also have a launch of an urban teammate, which would have both the chauffeur and Guardian. So, gulp, this is getting real. 10 million cars a year. So the way you usually launch things is you put it in your flagship car, for us the Lexus. So that's sort of the premium thing. And then a few years later, it gets into the Camry, and a few years after that, it comes into the Corolla, like that. So it's not 10 million right away, but that's our charter. So that's kind of a snapshot of what's been going on. Let me focus now on robotics, which is something that I'm more directly involved with. Toyota started as a textile machinery company. It made looms. They were the best looms. They were able to sense when it dropped a stitch. Other looms would make an error and then keep going, and then you're done. You look at it and say, I dropped a stitch. And the Toyota loom would detect it and stop. And someone would run out, fix it, and then start it all up again. 1936, Koichiro Toyota sold the company and did a big pivot to cars. He had gone on a trip to sell looms in the United States, and he went to New York City and he saw all these cars. And he said, that's the future. That's what I'm going to do. And this is the 1936 Model AA. In the 1990s, Toyota came out with the Prius, a revolutionary electric car, the first one. Right now, this is this year's Lexus. I think it's beautiful. Other people gripe about the grille, but I'm gonna take it. And the question that TRI, that's all TMC. It seems likely that we're going to sell fewer cars in the future with mobility as a service and ride sharing and aging society, less people buying and owning cars. So what's Toyota going to do? What's the next pivot? We went from textile to car to robots is what TRI's hypothesis is, and we're working to make it possible for Toyota. It seems like every generation of the Toyota family wants the company to pivot a little bit. So this would be the legacy for Akio Toyota. So we are taking head on what I think is our society's biggest problem, which is aging. And just to this is the age, and this is the number of people. So at age 70, this blue line is year 2008, 2 million people. In 2030, double, 4 million people in the United States. I showed you those graphs like this for the Japan population, and you can look at the China ones. They're all getting many, many older people. And this has lots and lots of ramifications, for our healthcare system, transportation system, and we want to address this problem by allowing people to age in place, to allowing older adults to have a full life without having to go to a care facility or a nursing home or a hospital or a hospice. I guess the hospice we can't help. But that is kind of what I want to focus our robotics on. And we want to get our cars out in a few years, 2020. The robotics can wait a little longer. This crisis is slowly happening, but we have a little more time. And I think it's more like a 5 to 10 year horizon is when I would like to be able to stick my finger in the dike and hold back the flood of aging a little bit. So one of the key approaches that we have for doing this is simulation. And Google and Berkeley's Sergey Levine has his ARM farm. Well, we've got a virtual ARM farm. And what TRI has is the world's best simulator now, called Drake. And it's an open source. We haven't officially launched it yet, but the ability, all these robots is exactly the same robot doing exactly the same task, picking up that blue thing. They drop it, goes into some random orientation, they try to pick it up again. So this is running up in the cloud, lots and lots of robots, many, many samples, and we then study the errors. and the distributions, find the statistics of the failure distributions. And then you know what's going wrong, you fix that problem, and then try it on physical robots. Physical robot is never exactly the same as the simulated one. Update your models from the physical robots and plug that back in. Every time, and we are having a real sort of modern software approach to this, so that when you find a problem, it wasn't able to pick up the blue funnel thing, in such and such an orientation and such a starting configuration, then we put that into the testing. And when we do our continuous integration, so we build our software every night, and it's got to pass that test before we promote that software to our master branch. So the volume of testing and the quality of testing that we can do with the cloud and our simulated system is just way, way more than you can ever do with 1, 10, 100, even 1,000 physical robots. And it's a virtuous cycle between the simulation and the reality, the physical robots. The cloud is also, when one robot, say in the United States, discovers a new behavior or a new ability to pick up that blue object, or patches a bug in the software that was picking up that blue object, and you update the servers on the cloud, then all of the Toyota robots in Japan, all through the United States, all around the world, get that same update right away. And the ability for that to basically have an over-the-air update is another big part of our strategy. So we're not just doing things in simulation. Here is our new facility in Cambridge. I saw some demonstrations here similar to this. This robot in the foreground has a RGBD sensor. It does a pass like that over the pile. It doesn't have any models. It doesn't know any of those objects. It just makes a point cloud, segments the point cloud, finds something on top, and then tries to approach it and pick it up. It doesn't always work, and it doesn't always put it in the yellow bucket the way it should.
Are you guys, should I say, emotionally against models?
Emotionally against models? Not at all. This uses models of the robot, but it doesn't require models of the object.
But you are
We've scanned.
emotionally, so you are not in principle
No.
against. So for example, you come from computer vision, so you know how to do this.
We've scanned all those objects, and we also have systems that try to you do the point cloud and try to segment out specific objects, recognize them, and then it's object 14. I know that behavior 37 is the one I should use for that object.
Ken Goldberg, I'm sure he showed you, he has this big cloud.
And the robots in back here were doing pick and place. So the simulation and reality together. That's not the one. That's not what I thought I was going to show, but here it is. We're also doing research on soft sensors. So this is a foamy piece of plastic. There's a range sensor underneath it looking up, and here is the image that it has, and we're able to analyze that and find the shape and the orientation of that object.
Caroline, did you show him what you have? We have similar systems. Good.
Ours is better.
I am sure, because, we do it on $5,000. You are doing it on $50,000. That's a big difference.
Yeah, she had a chance to see this herself when she came to RSS in Cambridge.
I didn't get to see it. I read too late.
Oh, okay.
It's cool.
And the project now is to miniaturize that and put it on fingertips, and the sensing part of it. And you can make very low-cost sensors like that, but the minimum range is the limitation. And they all have an offset of centimeters, and that's not going to work in the fingertip. And ultimately, we want to cover the whole body with that kind of a skin and be able to blindly touch, bump into things, be aware of them, and not have that be an error condition. It's just another way to interact with the object. So there's a group of maybe 3 people in our Cambridge office developing these sensors and coming up in simulation, pretending that we have a small one and decorating the body and of the arm and the torso with all of them, and figuring out how to close feedback loops around. It's not just tactile, right? It's really dense geometry that we're getting out of this. It's not just a few points of tactile. And you can, in a sense, you get the whole pressure distribution, the forces spread over the entire contact area. And it's not obvious how to use that in grasping and manipulation. It's a much more, it's a higher dimensional feedback loop.
I cannot resist to say that you remember the Toulouse finger,
Oh, sure.
right? Ideas were there. I'm talking about folks in the 70s, and Eric actually spent some time in Toulouse, working with these people. We had this, I hate to say this, it was called French finger, but it looked like a penis.
Yeah, unmistakable.
Anyway, go ahead, please.
So here's another one where, usually when the rest of your hand or rest of your arm hits something, that's an error. So here's the simulation in Drake, and here's reality. The guy walked by to show you it's all really in real time. I think you'll notice a very good agreement between the simulation and the physical manipulation here. And you can see the little force vectors coming out there. I'm going to play it again because it's short. The idea of whole body manipulation and multiple contacts, we relish that now. It's not something to be avoided. And actually, the more contact you have, the more stable the entire system can be. And to sort of hug things. So this is a direction, and in the home, interacting with people, we think this is going to be very important. So one other area that we are researching is manufacturing, and I've been to many of the car manufacturing plants, and we looked at all the things that people were doing and how could we help the people be more effective, safer, and assembly seemed to be the most promising thing. So we're now applying robots to helping to assemble different pieces of the car. So here's 2 guys putting this rubber weather strip into a window frame. So you have to hold it up there and you scoot your fingers in, and it's like this. And it's kind of a awkward thing to do, and it's 2 people, 2 arms each. So there's lots of ways to cheat this, which we've been having fun exploring with, like heat the weather strip up and let the elasticity of the material So you don't have to push it up and wedge it in as hard. It kind of naturally does that, and as it cools, it sets in place. And coming up with different end effectors, like something that vibrates it into place instead of doing what a person would do. Or also another problem is when you manufacture the chassis, there are these holes and you have to go plug them up, otherwise water gets in. And so you have to insert these plugs into various, and so we've made sort of a fixture, and we now have the robot plugging, putting the plugs in. Some of them are very hard to reach, which makes it awkward and causes back and thumb injuries. And cable harnesses is a huge problem. They're very awkward, and there's lots of them. So being able to mate a plug and a receptacle makes it sound very simple, but it's a lot harder than plugging into a 3-prong outlet. So those are some of the manufacturing tasks that we're taking on. And if this is a bar chart, right, home is like this and factory is like this. This is a much bigger problem, and we're putting more of our resources on it. And assembly is it's kind of like we can't be part of a car company and not do something for car manufacturing. That is what I wanted to tell you about our robotics program, and I'm going to switch now to talk about the university program just a tiny bit. So those are the 3 institutions. We have something like 45 projects, probably 50 or 60 faculty, PI, and 100 or more grad students and postdocs that are working on projects. And for each one, there is a TRI liaison who is essentially part of their lab. You go to the lab meetings, and at our next big workshop meeting where all 3 universities get together with us, we're going to make our TRI people give the PI's talk. We'll see how that goes. And the papers are starting to just pour out. There's no question that the quality of the work is good. They get it. We want to do driving, we want to do robotics, we want to do materials, but now coupling the progress at those universities into the rest of TRI is an art, and it doesn't have to be that good. And an example, a guy who I consider a demigod, Bertold Horn, like in Baichi's computer vision class, that was the textbook. And he's part of the MIT program, and he's coming up with these beautiful models of traffic. And like looking at waves in traffic and different oscillations and dynamical systems. And it's like, I can't even follow it, and we'll never be able to use it, but Bertold, you go. And he's publishing in SciAm and, all these applied math journals. And
congratulations, because about a year ago I communicated with him. We exchanged Christmas cards and he said, Ruzhna, I'm done with academia, writing proposals and all that. I'm retiring. And he was asking me, I said, I'm not.
well, I don't think he was telling you the whole story there.
All right, I'm happy to hear that.
He's still quite active. We have a weekly seminar at each of the places, and like on Wednesday afternoon in Cambridge, 12 people walk over to the AI lab. And next month, all of the professors are coming to TRI, and we're going to show off the robots and, open house. So this program, and we're getting interns. We have a very big intern program. It was 15 people last year. It's going to be more like 30 this year. So this is a great way if you want to work at TRI, but don't necessarily want to get a job yet. That would be a good way to start wading in. This is going to be the last chart here. Our materials program is about applying AI to the design and discovery of materials rather than like the chemistry and physics of the materials themselves. So we have a consortium of all the top universities, all listed here. That's Lawrence Berkeley Lab. Close. And, you know, I think we've already got a Nature paper in like 6 months. We are building our own sort of internal small team, and it's people who are quantum chemists and physicists who all have sort of a computational mindset, and then a bunch of data scientists, and that are curating all of the databases that we then apply learning and knowledge representation to. And the whole point of this is to be able to speed up the discovery of new materials. For example, for batteries, which is a huge part for electric vehicles and for fuel cells. And this is kind of the focus problems for our materials effort. You know, so it's not hardcore material science. We don't have benches with people making materials. The rest of Toyota does. We're the AI part of it. I think that is it. So I would like to stop here and see what else you guys want to know.
So let's thank Eric. Okay, and if those of you who do want to ask questions for our remote viewers could also use the microphone. So does anybody want to? I have a question to start. Actually, so I thought the paradigm with the sort of driving program was pretty nice. You have this guardian and this chauffeur sort of, you know, abstraction of things that I think works really well. I was curious if you had any similar sort of analogy for where you think the homework, the home robotics work is going, because I think that's a little bit more of a really difficult nebulous problem to get a hand on, and where you think the first applications will actually happen. In terms of actual, you know, seeing the light of day.
I don't think the chauffeur and guardian framework applies that well to a home robot. There is sort of a layer of supervisory control. You could imagine I'm your home robot and you've asked me to put away the groceries, and I'm starting to do that. And the rest of the house has, you know, a network of sensors and recognizes, the robot doesn't know it, but the house does. Oh boy, the Cub Scouts troop is coming in, and they're all going for the kitchen because it's snack time. So robot, you know, disappear, get out of their way. So there's higher levels of control that you could think of as like guardian that are watching over the robot and alerting it to things that it's not aware of.
Yeah. So I think also I don't want to, like, I don't think my question is really super like that those two paradigms apply particularly well to the home robots. I think I was just curious whether you had any similar intuition for you know, when these systems actually reach people's homes. I think there's this idea of, you know, Rosie the robot comes in and cleans up your house, and we have these sort of cartoon versions of what that looks like. But I was curious whether you had any intuition for what those robots in their first iteration would actually start to look like, and what sort of tasks they'd be able to handle, and whether there are any nice abstractions that you could draw.
So I have answers to that.
proprietary?
I'm not able to talk about all of them, but the activities of daily living, bathing, toileting, grooming, dressing, is one thing that like people all over the world do, and the instrumental activities of daily living, where you use the telephone, the computer, the vacuum cleaner, the blender, the refrigerator. You use those instruments to get a job done. That's the class of task that we think we could do in a few years with modern robot technology. And manipulation is a key part of that. We're not going to get into the conversational agent, you know, a better Siri or Google Home or Alexa. They're doing great, and we need that. But things that can really do work, applying forces and torques on the environment, I think is where we're really headed.
Awesome, thank you.
And I would go, you know, I said highway teammate than urban teammate. I'm advocating, and this is just Eric, this, if you're gonna, don't say this is Toyota's plan. Eric's idea is we would have the home teammate in the late 2020s.
Awesome, thank you.
There was a question.
Yeah, well, I think Ron and I crossed.
Thanks very much, Chair. So can I ask why that type of gripper? Why that doesn't seem like it's going to be very well suited for the home? Like I'm going to have trouble with the doorknob, for example.
Yeah, the parallel jaw gripper, right. We have families of grippers. These are just the simplest ones that were already instrumented with the IWA arms that we were using. And you know, the Robotique, 3-fingered one, and there's an old iRobot design.
So you're using them, but just not, it's not a video.
Right. And we're not going after suction.
So airlines have been automating as well, and I guess a big paradigm there is compared to Guardian. The airplane does the easy stuff, and the pilot takes over if there's a crisis. You're doing the opposite with Guardian. Can you comment on that a bit, or why do you think one might work better in the car than in the airplane?
Well, I think there isn't really a Guardian function. The autopilot is basically the chauffeur function. And when things go crazy, it says help, and you know, a pilot, you have to take over, and that's the handoff problem. And there have been lots of studies of that when the pilot's not paying attention, and you're about to stall, and you don't know what all the other environmental variables are. The pilots jump in and they have to do something. They're not ready to do it. They make big mistakes. So. I don't think the airline systems have a Guardian-like function. That might be a good thing to add.
The pilot is the Guardian.
In principle, you're feeling very charitable. I think the airline industry is a very good comparison, though, for thinking about how automation is going to affect, you know, and ripple through the transportation system. It's also, you know, probably the biggest barriers to this stuff really seeing reality, seeing financial and commercial reality, is legal and regulatory. And, you know, the insurance companies, and how that has played out with the airlines, I think is very instructive, a good model for us.
At least from the example you presented for robotics, I got impression that at least the current emphasis may be industrial robot utilization for Toyota company, and maybe a sign that Toyota is frustrated by robot manufacturers solving their problems. Is that some good observation, or it's not really?
I certainly cannot speak for the Toyota Motor Company. I did show you industrial arms, but that is because they're very easy to use, and we can get our experimentation going rapidly. But we don't expect those arms to really be used in a home. And those arms cost $100,000. And we think, you know, it's more like $1,000 would be a target for a 7 degree of freedom arm, roughly $100 per degree of freedom. So we are definitely focused on the home, and those videos with industrial arms don't give the right impression. When I have visited the Toyota plants in Kentucky, Ontario, and Takaoka, I talked with many, many people in management, on the floor, in the supply chain, and everyone was enthusiastic about robots. No one thought, oh, it's going to take my job, or something's wrong with the existing robots. No, they wanted more, and everybody's focused on quality. quality and safety and fewer injuries. And getting robots to do things that people are getting injured in their back or their thumb, they wanted more. So they were very enthusiastic about that. I hope that answered your question.
Any other questions? All right, awesome. Well, let's thank Dr. Krotkov one more time. And thanks everybody for coming.